Today's topic is statistical process control. So we're going to explain statistical process control, process capability, and especially we're going to explain the control charts, R chart, Xbar chart, P chart, C chart. We're going to explain capability and compute CP and CPK. So statistical process control. The objective of the process control system is to provide a statistical signal when assignable causes of variation are present. So again, I remind you that variation is against a decision maker's accuracy of decision, and the higher the variation of numbers in process, the more difficult to put the system in control. So our long-term goal is to observe the system, make sure we create an upper bound, lower bound for our process variation, and if everything is in control, then all those numbers, all those variables or values will be between upper bound and lower bound. If anything goes wrong, those will be higher or lower than upper bound and lower bound. So imagine we are talking about, for example, an airport, right? Every day 1,000 flights go and come, and seconds matter, minutes matter, and the second that an airplane is going to take off or lands, these are all calculated. If anything goes wrong, then there will be a lot of problem happening. Scheduling is very important, making sure that people are arranged, the timing is arranged well. All of these require perfect timing, right? So let's say flights, of course, flights can have delay, but even delay of flights should be controlled. We need to make sure, for example, there's not any flight that has more than 5 minutes of delay, or leaving early, right? Because these can be problem to the whole system, and one delay can bring more delay to the whole system. As a result, we can put this control in the system and monitor delays of flights, and if a flight has delay, for example, more than 5 minutes, we immediately check and see what's happening, what's going on, and of course that's going to help us to resolve the problem as soon as possible. Variability is inherent in every process, and that's something that's out of our control. Natural or common causes are available and bring this variability. Special or assignable causes are also available. So we always need to be aware of causes on variability, because if anything goes out of control, if any failure happens, we can always look at those causes and immediately know where to go and where to fix the problem. Provides a statistical signal when assignable causes are present. So we're talking about the statistical process control. So statistical process control provides a statistical signal when assignable causes are present. Quickens appropriate action to eliminate assignable causes. So natural variation, also called common cause, affects virtually all production processes. Expected amount of variation, an expected amount is what we can actually in average calculate it. Output measures follow a probability distribution. So since they are natural, many of them follow normal probability distribution or other types of probability distribution, such as Poisson distribution or beta distribution or alpha distribution. For any distribution, there is a measure of central tendency and dispersion. So, and what we mean here is how this variation is distributed. Are most varieties of things occurring close to the average, around the average, or are they very far from the average? So that tells us about the distribution, and statistical we can find out what distribution we are using. So remember that normal distribution is the most useful distribution for us, especially for natural variations. If the distribution of outputs fall within acceptable limits, the upper bound and lower bound that I told you we will calculate, the process is said to be in control. Assignable variation. So it's also called special causes of variation. Generally, this is some change in the process, variation that can be traced to a specific reason. The objective is to discover when assignable causes are present and eliminate the bad causes, inappropriate the good causes. So this is an example of, so to measure the process, we take samples, right, and analyze the sample statistics following these steps. So samples of the product, say 5 boxes of cereal taken off the filling machine line, vary from each other in weight. So it's important for us because we don't want to have overfill our boxes. We also don't want to have less than what is supposed to be in the box. As a result, we have to weight them, right? Weight them to see we're not selling more than what we are supposed to sell for the price we're getting, and we want to make sure customers are happy, so we don't want to put less than what's supposed to be in the box. But again, variation exists, so we can't put time and weight every box coming out. So we get a sample. In that sample, let's say we produce 1,000 boxes every day. We take a sample of 200 or 100, and that sample actually represents the population, and by studying it we can understand how other boxes are changing in weight. So you can see that we have created a normal distribution, and that normal distribution is happening because center will be the average weight of a box, and you can see majority of the boxes are around average, right? That's why I say normality is very good for managers, because in normality, majority of cases are actually giving you values close to the average, and if you make a decision based on average, you're making decision for majority of cases. And this also helps us if a box is having a very low weight or high weight, we can actually see it and find it. So to measure the process, we take samples and analyze sample statistics following these steps, right? So you can see that if we have a perfect normal distribution, we can actually statistically explain a lot of things and put a control limit around it. So not every sample we take is perfectly normal. Some of them have high variation. High variation means maybe too flat or too high, or maybe skewed to the right or skewed to the left, or the average is actually higher or lower than what we expected or what we calculated based on average. But why do we like normally distributed data or samples? Because normal samples, you can see, they are similar. They're producing similar behaviors. And this way you can, in management, prediction is very important. So if you have, by time, you can see that the behavior is almost the same in a normal way. You can predict that this behavior is going to be there the next time and the next time and the next time. So by predicting certain values for the future, you can actually manage the future, right? So that's very important for us. But on the other hand, if you have data collected from the past, and at different times or seasons you have different shapes of normality, right? Some of them have too much height, or skewed, or normal, or not normal, or flat, and then it's very difficult to predict the future behaviors, and if you can't predict the future behaviors, it's difficult to manage everything in the future. So that's why normality actually is very important for us. Control chart. So constructed from historical data. So we collect the data, right? And we use this data to put an upper bound and lower bound. The purpose of the control chart is to help distinguish between natural variation and variation due to the assignable causes. Process control. So you can see that in statistical control and capable of producing within control limits. Every time everything is in control and happening almost in the same way, right? Almost in the same quality, same timing, same number of production, same number of people being processed, or number of customers being served, right? That's the perfect thing that we want. But in statistical control, but not capable of producing within the control limits. So they seem pretty much the same, but they're out of control. Maybe flights that their delay is more than 5 minutes. It's not happening to one case. Every day, every flight has more than 5 minutes delay. So that would be this case. Is that okay? The answer is no. So that system is out of control. Our system is completely out of control. Not only the shapes are not the same, but also they're out of the control limits, but they create different shapes and they have complexity. So these two are not what we want. This is what we want. We want the system to be completely in control. Okay, so control charts for variables, characteristics that can take any real value. So we need to take factors into account that actual numbers can be used, right? Not words, actual numbers. So numerical variables are required, maybe in whole or in fraction number. And they have to be continuous random variables, right? Because that will give us that normal distribution. That's how we can calculate average or range. But if these numbers are not continuous random variable, then it's not possible to create a control chart. So for having a control chart, we need to make sure we have a continuous random variable and numerical. What is Xbar chart? Xbar chart tracks changes in the central tendency. And what's the difference between central tendency and dispersion? So dispersion shows distribution of values, how they are distributed around average. But tendency shows a point. So average shows a point. So with Xbar represents average. Average shows a center, a point, and based on that point, we want to find out how others are behaving. But in our chart, which includes a range of values, R for range, our chart looks at the ranges, and range shows how the data has distributed. It shows what's the lowest, what's the highest. That's the range. Everything else is in between. So knowing the range can help you to know how the data is distributed, right? If I tell you we have a class of students in the range of 18 to 25, then you know where they stand, right? But if I just tell you that average age of class is, for example, 25 years old, it's difficult to say how they are arranged, because you just have one point, you just have one central tendency. So do we need different charts? The answer is yes, we need both charts. Xbar chart and R chart to make decision about control charts, about the system to be in control or not. So these two charts must be used together. Okay, so we look at both to make decisions, not just one. So what is Xbar bar chart? This is Xbar bar. There's two bars, right? So average of averages. Each bar represents average. So Xbar bar is average of averages. So you get a sample, and for that sample, let's say you have 10 days of flight delays. Each day you get 10 samples. Check delay of 10 flights. So basically your sample size is 10. Then you get the average delay of that day. Then you get the average delay of day 2, day 3, day 4. Let's say 100 days, right? So each day 10. So you have 100 days. So each day you have an average. Then you get the average of the 100 days. That will be the average of the averages, right? That is Xbar bar. So Xbar bar is average of your averages, average samples. So the mean of the sampling distribution will be the same as the population mean. So when we calculate this average of averages, it will have actually the same mean or the same average as the population. So what is this topic? This topic is central limit theorem, right? The central limit theorem says that if you collect samples from a population, smaller samples with a specific size of n, then let's say you have 100 days, right? But from each day you want to take 10 samples. So such sample would be normally distributed, first of all. Second, first, the larger the samples you take, the better the normality. And also, the average of such sample is exactly the same as the population's average. So the average doesn't change because we took samples and took average of these samples. Standard deviation also would be pretty much close, but a little different. So standard deviation or variance will be standard deviation divided by radical n. So that's the only difference here. There's a radical n difference here. Okay, so we have, so if the standard deviation is given to you, remember that you need to calculate the standard deviation of the sample mean. If the standard deviation of sample mean is given, you don't have to do anything, you just use for calculation. So it doesn't matter what type of data you have, they follow beta distribution, they follow normal, uniform, or other distributions. Getting a sample, getting multiple samples and getting the averages will convert these different distributions into a normal distribution. And having a normal distribution can help us in creating the control charts. The rules that you learned before, 2 times standard deviation includes 2 times standard deviation away from the mean includes 95% of your observations. 3 times 99.7%, right? 1 time 68%. So you can see that here, and you have learned that in the past in statistics. So this is process distribution of means, and when you get a sample, you will have a better normality. Majority of data, you can see that those that they were out, they become a part of that curve. So that's central limit theorem. You can get smaller samples and get the average of those smaller samples and get the average of averages, and that creates a normally distributed data. Okay, so the larger the samples you take, the higher the height of this normal distribution, the better the normality, closer to normality. Especially after 30 samples. If your sample is more than 30, then you will have a perfect normality above, no matter what your initial distribution is. Okay, so next is chart limit. So for Xbar charts, so its name is very obvious that you're going to use Xbar, and Xbar means average, right? So you're going to use Xbar as the center of your chart, and you will have upper bound and lower bound around it. So how do I calculate, where do I get from these upper and lower bounds from, right? So I'm going to calculate based on the 95%, 99% standard deviation that I just explained. So if you want a control chart with 95% confidence level, you calculate the standard deviation, and using that standard deviation plus 2 times of it, you will have 95%. Plus minus 3 times of it, you will have 99% confidence level. So in this formula, you can see the upper control limit. So if you have learned the confidence level in the past and the confidence formula, I can say that if you do that, if you have learned the confidence level well, then I can say that this will be very easy for you. Okay. So the formula is this: upper control limit, Xbar bar, plus Z. Z is 2 times or 3 times, right? This normally is given to you, or we will give you, or we will tell you use 95 or 99%. So then you will change it to 2 or 3. And standard deviation will be given to you. So you just plug in the numbers, plus minus. Plus will give you the higher part of the chart, and minus will give you the lower bound. Okay, so this is a numerical example. In this numerical example, we have randomly selected and weight 9 boxes for each hour. So instead of days, for each day we select samples. Here we are taking samples every hour. So every hour, how many samples? 9 samples. So sample size here is 9. Remember, this is where many students get confused on exams or homework, and their calculations go wrong. So it's very important to recognize what do we mean when we say sample size 9. So what we mean here actually is if we have 10 different days, 10 different hours, 10 different sections, right? For each, how many samples you're taking. So in this case, 9 samples, 9 boxes per hour. The first hour, we collect randomly 9 boxes, and we want to see what's the weight. 16.1. And how we got the 16.1? You can see the calculation right here. So the first box we took has 17, weight 13, 16, 18, and then we get the average 16.1. The second hour, another 9 boxes are taken out and weighted. The third hour, the same. The fourth hour, the same. That goes up to 12 hours. So for 12 hours, we take 9 samples each hour. Right? What's the sample size here? Okay, so now if I get the average of these average, each of these numbers is average of that hour, right? So if I get average of all these averages, what would that be? Xbar bar, right? So Xbar bar, or average mean of the 12 samples, is the average of 9 boxes divided by 12. Right? Let's go down here. Now let's run some calculations. So the question here will normally tell you, are we looking for 99.7% of confidence level, or it will tell you use Z equal to 3. one of these is given to you. So I believe this semester, I can say like among every 10 questions, 7 of them, all this information is given. 3 of them, you will have to look at the z-chart and find the numbers, but that's just few cases. It's not a lot. Okay. So let's say here the z value is given 3, or we were asked to use a 99.7% of confidence level. As a result, Xbar is 16. We just saw the calculations. Plus minus. Plus will give you the upper bound. Minus will give you the lower bound. 3 is your how many standard deviations away from mean? 3 times. And 1 over radical n. And n here is 9 because we took 9 samples, right? So we just calculate 16 plus minus 3 over 3, that's 1. 16 plus 1, 17. 16 minus 1, 15. So the control charts, the upper and lower bound here are our boxes need to weigh between 15 to 17 ounces. Alright, so setting the control limits. So we just calculated the control limits, upper bound 17, lower bound 15, and we calculated the Xbar, the average of the averages, as 16. So we put 16 as our expected value. That's what we expect to have the weights, but they're not supposed to be as far as more than 17 or less than 50 ounces, right? So if we keep weighting all of these boxes during the time and they're always in between the upper bound and lower bound, we're good. The system is in control. If for any reason one of these points is outside the range, we say the system is out of control, and that's where we have to look at the causes and see what has caused this out of control here or out of control down here, and immediately go and fix that problem in the system, and the system goes back to become in control again. Okay, so that's actually very important. You can say this can be automated. You can create a system that automatically collect data, collect the information, or a person manually enters every hour, enters the information, and the system, the computer calculates. As soon as anywhere the system is going out of control, it will warn you, and you will think about solution. Okay. So the previous formula that we saw, we used sigma, we used standard deviation sigma. So what if the information of sigma is not provided? If we don't have access to it, we cannot calculate it. We just have the minimum and maximum. If you only have minimum and maximum, then we can use range. Range is equal to max minus mean, right? So we calculate the range for each case, for each day, for each hour. And for that day or hour, we have one range, right? So, and then we calculate the average of these ranges. That become R bar. So what is R bar? R bar is average of the range of each day or each hour or each time. Okay, depending on how we collect our data. What is A2? So A2 is a number very similar to what you learn in standard deviation, but it's actually the value is actually provided to you. So if your sample size is 2, A, based on how many samples you have, 1.8 up to 12, right, is given. So examples we will give you, they won't have any number outside this range. If it has, the table will be provided to you for that specific sample size. So you won't have to be worried about that. This number, you will get it from us, right? So A2 is for Xbar chart with the range values. Xbar chart with the range values. D4 and D3 are for R bar, not Xbar, Xbar chart. Okay. So again, going back here, So you know R bar is average of range values. A2 you get it from the table. What is Xbar bar? It's the same. It's average of averages. So you got the averages. This is given to you. Ranges are given to you. You calculate the R bar. A2 you get it from the table. You just plug it into this formula and you calculate upper bound and lower bound. Upper control limit, lower control limit of Xbar. Okay, I can see that R bar equals to, so we have K different samples, different days or hours, and Ri represents range of sample, each sample. Divide by number of days or hours. A2 comes from the table. Xbar bar is the average of the sample means, and each Ri is a range of each sample, and this is the total number of samples. So that's the table I told you. You will take numbers from it. So let's see an example. Alright, so in this example we can see that we have super cola, and we are weighing 12 ounces, right? Process average is 12. That means Xbar bar is 12. Sometimes the question will give you population's average, which is the same as Xbar bar. Average range is, so range of averages, average of the ranges is actually calculated and given to us. So we don't have to calculate. This is already given. If it's not given, you will calculate. So that's given to us. The only thing is left is I need the A number, right? Where do I get the A number? From the table. How do I know from that table which one of these I should take? I need to look at the sample size, right? So what's the sample size for that case? 5. And what's the A? 2.577. 0.577. Plug it in. 1 time plus, 1 time minus. Plus will give you the upper bound, minus will give you the lower bound. Alright, next is R chart or range chart, right? So type of variable is a type of variables control chart, shows sample ranges over time, and that's the difference between the smallest and largest value in the sample, and it monitors process variability, and it's independent from process average. So average is not. So one sign that you can use the R chart is you don't have average. In the previous Xbar charts, both with the standard deviation and with the range, they both had Xbar as a central tendency, right? But here you don't have Xbar at all, right? So that's a good sign to know you need to use a R chart. So to calculate the R chart upper and lower control limits, R bar is either given to you or the data is given and you can calculate the ranges and find their averages. And then you need the how many standard deviation or how many D's away from the center, right? So that would be D4 and D3. Where do you get D4 and D3? We just learned from that table. So A2 was for earlier formula, D3 and D4 are provided in this table. So our chart gets its D values from this chart. And again, this chart will be provided to you, especially if you have more than 12 cases, you will have access to. And that's it. So I think our chart is pretty much easy to calculate. So let's say we have a restaurant control limits and average sample mean here is 10 with a upper limit of 11.5, lower limit of 10.3, and here we have our chart, right? So do you think this system is in control or the system is not in control? Alright, again, so you can see that this Control chart shows that the system is out of control. One reason is your Xbar chart shows that point is on the lower bound, so it's clear that the system is out of control based on Xbar chart, and based on range chart you can see that on the same day or the same hour we have a point or average of that day out of control, outside or higher than the upper bound. So the system in general is out of control. Okay, so let's say we have average range in a system to be 8 minutes with a sample size of 4, and from table that we provide a D value, D4 is 2.282, D3 is 0. Let's see if these numbers are correct. So sample size of 4, going back up, looking at that table, 4, 2.282, and the lower bound is 0, so it's between 0 to 2.282. Okay, so we just need to plug in the numbers. For the lower bound we have 0 times 8, which is 0, so lower bound is 0. Upper bound, we can see that it's 18.256, but I want you to calculate it. So spend maybe 2-3 minutes maximum and calculate. Make sure you get this number right. Use your calculator and get this number, upper bound. See if you can do it. Mean and range charts. So you can see the difference here. So these sampling distributions result in charts below. Sampling mean is shifting upward, but the range is consistent. So you can see we have the same distribution, right? Same range. Range is not changing, but the average is changing, is increasing. So Xbar chart shows the system goes out of control. You can see that, because that's the average of each day or each hour that is increasing. But our chart shows that the system is in control. So it's very important that you remember whenever you're deciding on if the system is in control or out of control, you check both charts, both Xbar and R charts. Why? Because this can happen. If you just check our chart may show the system is in control, but Xbar chart is showing that the system is actually out of control, and you can see that the system is out of control. It's going beyond its upper bound, right? Let's see, we should have another case here. Here you can see that the average is not changing, it's the same average, but the range is changing. This system is also going out of control. This system is out of control, but Xbar chart shows that the system is perfectly in control. All these points are in almost the same place, right? If you only look at the Xbar chart, it will tell you that the system is in control. But look at the R chart, the range is changing, is going out of control. So in general, we can say the system is out of control. Again, always look at both charts, R chart and Xbar chart, to determine the system is in control or the system is out of control. Steps in building control charts. So I think you have learned this. It's pretty much simple, but I just read it one time really quick. So collect 20 to 25 samples, often samples of at least 4 or 5 observations in each, from a stable process, and compute the mean and range of each. Compute the overall means, Xbar bar and R bar. Set appropriate control limits, usually at 99.7%, which is 3 times standard deviation, and calculate the preliminary upper and lower control limits. If the process is not currently stable and in control, use desired mean instead of Xbar bar to calculate limits. You won't face any questions that you would have make such decision, but you can always actually do that if you need to. And what is mu? Mu is the population's average, and I told you that Xbar bar is the same, has to be the same as mu. So if you have the population's average, you don't have to use the sample's average, you can use the population's average. Step 3. Graph the sample means and range on their respective control charts and determine whether they fall outside acceptable limits. Investigate points or patterns that indicate the process is out of control. Try to assign causes for variation, address the causes, and then resume the process. Collect additional samples, and if necessary, revalidate the control limits using the new data. And reevaluating the control limits, meaning that even your average could change because you're using a new data set. A new data set may move your average and upper and lower limits. Next is control charts for attributes or qualitative or categorical variables. So for variables that are categorical, categories could be like defective or non-defective, good or bad, yes or no, acceptable or unacceptable. So these are groups. Measurement is typically counting defectives. Charts may measure percent of the defect. We call it a p-chart. Or number of defects. We call it C-chart. So p-chart and C-chart. P-chart counts defects and show it in percent. For example, if you have 100 samples, 3 cases, you got a sample of 100, 3 of them are defective. They're not working, or there's a failure in the system at that point. So that would be 3%, right? That's when we use a percent to represent the values, we use a p-chart. If you want to just say there are 3 defects, use the number 3, then that's a C-chart. Okay? So if you want to use a p-chart, P proportion, P is proportion, so or percent, right? So population will be a binomial distribution, but applying a central limit theorem allows us to assume a normal distribution for sample statistics. And since we are using a normal distribution, we can use the normal distribution formulas. So we can find P can be the average in percent, so mean fraction defective in the sample. Let's say we have 10 days and each day you collect 100 samples, and one day 3 of them, one day 5 of them, one day 10 of them are defective, and then get the average of these different days. That's P bar. If you have P bar and if you have the sample size, if you have P bar or sample size or number of observation in each sample, you can calculate the standard deviation for proportion. If you have the average of the defects in percent every at different times, and if you have the sample size, you can calculate the standard deviation. So in some questions the standard deviation is given to you. In some questions standard deviation is not given to you. You need to know which formula to use to calculate standard deviation for proportion. So for proportion, this is the formula. Radical P bar times 1 minus P bar over n, and n is sample size. And I told you what the sample size is, right? So all these numbers are actually given to you. Just plug it into formula, get your standard deviation, and if you have your standard deviation, we go back to the basic formula for confidence level, right? So Z, 2 times 4, Z is 2 for 95%, Z is 3 for 99.7%. Sometimes the question will tell you the exact value of Z, sometimes it just tells you the confidence level, 99.7, so you just substitute 3. That's it. So what is p-bar? Mean fraction defective in sample. Z is the number of standard deviations. Sigma is the standard deviation of sampling distribution. N is the sample size. Okay, so we have a P chart for data entry here. So what do we have? So we have 20 maybe different days or different hours, and we took samples. So how many samples? We got 100 samples. So each of these days we got 100 samples. Each of these days we got 100 samples, and we recorded number of defects. How many defects in that specific day or hour, right? So in this case 6. So what is the proportion of defects? 6%, because we got 100 samples for that day, and among the 100 samples for that day, 6 of them are 6 out of 100. That's 6%, or 6 hundredths. Day 2, we check the defects. There were 5 defects, 5%. Day 3, none, 0. Day 4, 1.01, 1%, and so on. So you can see there are 20 days. Each day, how many samples? Hundreds. What's the sample size? 100, right? So, and these numbers are actually the p-values. So when you get the average of these proportions, that would be your p-bar, right? So what's your p-bar? You add up those numbers, they're 80. You can see the sum of these is 80. That's where the 80 come from. Added number of errors, number of defects. Divide by the sample size, right? So the total number of samples. So 20 different days, each day 100 samples, that's 2,000. So that's 80 over 2,000. 80 over 2,000. That's 0.04. So p-bar is 0.04, and all you have to do is to calculate the standard deviation. And standard deviation of proportion is p-bar times 1 minus p-bar over n on the radical. Okay, so 0.04 times 1 minus 0.04 divided by 100. That's how many samples you take every day or every hour. And that would give you, on the radical, that would give you 0.02, which is rounded from 0.0196. So for rounding on exams, on homework questions, the question will tell you how many digits to round to, okay, how many decimals. Alright, so we have all the numbers we need. We have a p-bar, we have z value, and we have sigma. So p-bar plus 3 times for 99.7% of 0.02 is 0.1. The lower point is negative. It doesn't make sense in this case. For number of defects, we can't have less than 0 because you don't have less than 0 production. So we shift it up to 0. So remember that for some question on exams, you might have this situation where a negative number on your control chart or on your P chart or C chart appears, and that number doesn't make sense. If that doesn't make sense, you might have two, in multiple choice questions, you might have two choices. One gives you the actual negative number, the other gives you with a 0. So if negative doesn't have a meaning there, you need to check the one with the 0. That would be your correct answer. Okay, so next is the C charts. So C charts, where you count number of defects. That's the difference between P chart and C chart. P chart, you record the proportion, percent. In C chart, you calculate actual number of defects, right? So Xbar is the average number of defects per unit. And the standard deviation of Xbar can be calculated just by getting its radical. So you don't need to add or subtract anything. No multiplication or division. You just get its radical. That's it. So I can say majority of questions that they require C-chart, the only thing that they give you is the Xbar. So if you have such question, and you might start thinking, so where is the standard deviation? Where is the R values? Where is the Xbar value? There's nothing given other than one value, and that value is Xbar. And Xbar, you just get this radical. That's your standard deviation. Plus minus 3 times of it, you will have upper and lower bound. So very simple. If you have 95%, you will have Xbar plus minus 2 times radical Xbar. Okay. See an example here. So we have Xbar as 54 complaints per 9 days. So this is not average per day. We need to recalculate it into average per day. So we divide it by 9, and that would be 6 complaints per day. So in average, so this is per unit, right? So here the unit is day, and we don't want, I know that the information is given to me based on number of complaints per 9 day, but I need to change it to per unit, and here unit are days, so I need per day. So for per day, in average, we have 6 complaints. And to calculate the standard deviation, you just need to get the radical of 6. Radical 6 is standard deviation, right? So mean, or Xbar, plus minus 3 times standard deviation. So this is standard deviation, radical 6. 6 plus minus, that would be 13.35. Lower bound is negative. Shift it up to 0 because it doesn't make sense. Okay, so that would be, so we don't have less than 0 complaints, right? That makes sense. So, and then we can graph the chart. And you can see that, so complaints, if we have no complaints, that's a good thing, right? So the lower bound is on the limit. So patterns in control charts, and what do they tell us? So sometimes the system is still in control, but by looking at the pattern, the system can tell us the system might be going out of control. So we always are looking for this up and down, right? Up and down. If it happens and 2 or 3, 4 times back to back, we don't have that up and down. Instead, we have up, 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 or down, down, down. This is a sign that the system can get out of control soon. So as a result, if you are working with future data and the system shows that instead of up and downs, you have up, up, up 3 times or 4 times back to back, even though the system is still in control, you can stop the system and look for the cause and see what's happening. And before the system gets out of control, like before having a flight, having a delay more than a certain amount that you don't want, you can make sure you get to know it before it happens, right? Find the cause. Maybe a worker is ill, someone is making a mistake in calculations in management, somewhere in the system one of the sensors is not working well. You can find it, and before the delay happens, you stop it, right? So this case is the difference. So we can see that you have the up and down, but immediately this is obvious. This is not a. This obviously you can see that the system is out of control. These are the ones that I told you the pattern. So you can see that it's going down, right? or two back-to-back are, instead of up and down, it's just going down. This can be a sign. Let's say this red line is the average. So you can see that in average they're moving up, right? So instead of having up and downs, you're having up, down, then up, up. So that's showing a pattern of the system going out of control. Same here, three back-to-back. They're moving up. One here, two, and three. So run the test, identify abnormalities in process, run 5 or 6 points above or below the target, or center line suggests assignable causes may be present. Process may not be statistical control. There are a variety of run tests. And the natural variation of process should be small, enough to produce products that meet the standard requires. So we're talking about the process capability here, okay? So process in a statistical control does not necessarily meet the design specifications. And that's normal, because when you design theoretically on paper, you calculate and design a system to work this way. In reality, always there are differences, there are changes that happens, and because of that the system is not necessarily always working exactly as designed, and that difference is what we're interested to know. How different is the system working compared to the actual design, and if it's far from it, there's a problem and it needs attention, okay? Process capability is the measure of the relationship between the natural variation of the process and the design specification. So, process capability ratio, we show it with the CP, and CP equals to upper specification or upper bound. This value is normally given to you. You don't need to calculate it. You will be also given a lower specification or lower bound. So the upper and lower values are given. Range, you can calculate it. That's the difference. That's the range divided by 6 times the sigma. And what is sigma? Sigma is standard deviation. So standard deviation is given. Upper and lower bands are given. Divided by 6 times sigma. That would give you the CP. So how do you know that this system is capable or it's not? You will look at the CP value. If the CP value is at least 1, the system is capable. So a capable process must have a CP of at least 1. Right? 1 or higher, the system is capable. Does not look at how well the process is centered in the specification range. It's just telling you that we are having that capability or not. So no analysis of values in between. Often target value of CP 1.33 is used to allow for off-center processes, and the question will tell you if that's the case. My questions normally won't. Okay, it's either 1 that I'm looking at, or I sometimes look at the 2.0. So if 6 sigma quality is required, you remember 6 sigma, right? Companies that they want to be accurate, like 3 errors in a million for those systems, and the question will tell you that if that's the case. For 6 sigma quality, we don't look at 1 or more than 1, we look at 2. Has to be 2. Or like 1.99 or 1.96. Somewhere very close to 2. That would say the system is capable based on 6 sigma. Process capability ratio, insurance claims process example. Process mean of Xbar is given to us, 210 minutes. That's the process time of insurance claim. Process standard deviation is also given to us, 0.5 of minute, 0.516 of minute. Design specification, that would be 210 plus minus 3. You can see that the CP is calculated. The upper specification is the 210 plus 3. The lower specification is 210 minus 3 minutes. Divide by 6 sigma to see if we have the answer here. So 210 plus 3, that's 213. And 210 minus 3, that's 207. Subtract the upper and lower specifications. Divide by 6 times sigma. Sigma is 0.516. The answer is 1.938. Okay, so I hope you got the numbers right. And the last topic will be Process Capability Index. The last topic for today is Process Capability Index. So the CPK, so see the difference. This is CP, Process Capability Ratio. This is Process Capability Index. Okay, it has a CPK, minimum of. So you will get the minimum of upper specification limit minus Xbar. So we don't want this to be negative. We want this to be positive. So the higher value minus lower value. If for any reason you forgot which one, you need to take the higher value minus the lower value. So upper specification minus Xbar, Xbar minus the lower specification. We just want to know the difference. And that's like using absolute value. Divide by 3 times sigma, which if you remember, that's for 99.7%, right? So a capable process must have a CPK of at least 1. These are different ways for you to check and see if a system is capable or not. A capable process is not necessarily in the center of the specification, but it falls within the specification limit at both extremes. Example, we have a new cutting machine and new process average is 0.25 inches. Process standard deviation is 5 and 10,000ths inches, 0.0005 inches. And upper specification is given to us, 0.251. Lower is 0.249. So what we need to do, we calculate both values and take the minimum as CPK. One is the upper minus the average. The other one is the average minus the lower value. And I think in this case they're the same, right? 251 minus 250 is 1/1000th. And 250 minus 249 is also 1/1000th. And 250 minus 0.249, they both have the same denominator, right? So let's see. Is that so the number that we calculated, the answer is 1/1000th, right? So you divide it by 3 times 0.0005. So the minimum doesn't matter. They both give you the same number, and then that same number is 0.67. So the 0.67, it has to be, the CPK has to be higher than 1 or higher than 1 for the system to be capable. So is this system capable? The answer is no, because the CPK is lower than